the last two modules we covered basic equations and vorticity, right. Now, I will cover conservation laws in the third module for hydrodynamics. Okay. So, we first we look at quadratic quantities, which are very important for describing fluid flows. Quadratic means product of two fields, and there are just with velocity we can construct several quadratic quantities. So, first one is kinetic energy density. So, I am going to be specific for the definition. Okay. So, U is a velocity field, right. So, we call half, I put a factor half, that is by convention, no. So, for particle of mass m, we half mv squared. So, similarly we just say kinetic energy density is half u squared. Now, density is 1, since density is constant I do not carry density. Okay. So, density is assumed to be 1, and this is in fact you can think of small. So, since u is changing everywhere, so u squared will change everywhere. So, you can think of, if I take a small volume dV, then energy contained in that volume will be half u squared times dV. Okay. So, that is why it is called density per unit volume, but the volume must be small. Okay. So, this is kinetic energy, which everybody knows, but it is important to keep in mind that this is definition. Kinetic helicity. So, we studied vorticity. So, using vorticity and velocity field, we can define some this helicity u dot omega and factor half, which some books may keep may not keep factor half, but in my notation I always keep half. So, half u dot omega. So, omega is a vector, please, omega is a vector. In 2D it is only along z direction, but it is a vector, is curl of u. So, u dot omega is a scalar. So, all these quantities are scalar, which I am going to cover today. And third one is called entropy, and which is half omega squared. So, curl of u squared. Okay. Now, you may say, why you have omega squared and u squared separately? It turns out it is useful to think of terms of omega on many occasions, which I will describe today, okay, a bit later. Now, given that we have density, we can also construct total kinetic energy in a volume. So, given a volume, you can construct total kinetic energy, okay, which is just integrate over volume. So, this means integrate over whole volume. Now, my volume could be a periodic box or a box with walls. So, the volume I have not specified, but total means over the whole volume. So, similarly, you can construct total kinetic helicity, which is again integral over the whole volume of u dot omega, factor half included. And similarly, for total entropy, it is this. So, density and total you must differentiate, and when I say conservation means for the total. So, u squared will change, but if I sum over whole volume, I will show that u squared total kinetic energy for some conditions will be conserved. Okay. So, now we have this quantity, so we can write down evolution equation for this. How does u squared change with time? Okay. So, that is my next objective, equation for kinetic energy density. Okay. So, I did not write it here, but kinetic energy density. So, how do I derive this? So, all this can be derived from Navier-Stokes equation, you can derive from the first principle. So, I have the Navier-Stokes equation, this one, right. I dot this with u. So, what is the first term, by the way? So, this is d by dt of u dot u by 2 by product rule. So, product will give you the first term. So, factor half in fact is useful to keep in definition. Now, what about the second term, this term u dot. So, this is a vector, by the way, please keep in mind this is a vector. In fact, ideally I should write like this, but in shorthand we do not want to write too many brackets. So, u dot grad is acting on first u, not on second u. Well, grad is acting on this, but a dot product is acting on first u and dot. Okay. So, this is a vector. Now, what is u dot grad u? So, it is easy to derive for incompressible flows. So, let me use tensor notation. Okay. So, tension notation is very useful, and you should just do some exercises. So, in fact, for some of my earlier derivation, I said curl of A cross B. Now, there is a big expression. Now, you can derive this from first principles or from using tensor analysis. So, that will be one of the exercises I am going to give you. Okay. So, I will show you how to do this for using with tensor analysis ui uj. So, I want to write this in tensor notation, ij notation. So, ui, and so this is a ith component, and this will dot with this. So, ui here. Now, by the way, no index should repeat more than twice. If you do it, then you are making a mistake. 2 means sum, and it already has been contracted. Now, you can't put another I, because that will be wrong. So, now I have another dot product between u and grad. So, what do I do with the u and grad? Should I use same i's index? No, I should not use the same different index, because 2 i's are already covered. So, use j uj del j. So, this is second index. You can use as many index you want, but dot means that those index should be repeated. Okay. Now, this is what I got. Now, so uj del j. Now, I can use product rule. So, this u squared. So, ui can go inside like this, because if I expand this, what will I get? You can expand this one. Okay. So, this expansion will be uj is silently sitting outside, del j ui plus same thing again. So, twice. Okay. So, you get again uj ui. So, I should put factor half. So, there are 2 of them. So, I should put half factor to get, no, not half, yeah, half here. So, I want to get this one. So, I put a factor half. So, this will same. So, this basically half of this will go away. Okay. Now, this is same as what I have written here. These two are equal. So, what is this object? U dot grad u. Now, uj del j is u dot grad, right, and this ui by 2 is u squared by 2. ui is a u squared, no, ux squared plus ui squared plus uj squared. So, this is u squared by 2. So, this is how you can derive quite easily using tensor notation. Now, what about the next term, minus grad p dot u? So, since u is a del, well, whether del dot u is 0, so this is what you should keep in mind, del dot u is 0. So, using del dot u I can simplify this further, this one can be simplified further. So, I think before I go to grad p dot u or u dot grad p, let me simplify further. Can I push u inside, u vector? For incompressible flows, can I push u inside? Yes, you can push inside. So, in fact, you start from here, okay, you start from here. So, this can be written as del j uj, and this is u squared by 2. In fact, this is a scalar quantity, this one. Now, apply a product rule again. So, one term is equal to that, and second term will be, if I expand this one, it is uj del j u squared by 2 plus u squared by 2 del j uj. And what is del j uj? 0 is del dot u. So, this goes away. So, these two, this one and these two are equal. So, in fact, you can write this object u dot this thing as divergence of u vector u squared by 2 dot. This is scalar, okay. Is that fine? Now, what about this u dot grad p? Can you go inside? So, I am interested in this versus this dot product. In fact, yes, it can go inside, because again you apply the product rule, you will find that del dot u is 0. So, this will be that, this term gives you this. Next term is u dot fu, keep same, and the last term is u dot nu grad square u. It is a viscous term which can be further simplified, which I will show you in below. So, I am going to erase this stuff, because I think some equation is going to appear below. So, this term is divergence of u squared by 2 u vector, this is what will appear, okay. So, these are two very important, this one and this one will play a very important role in conservation law. Okay? And I am not putting sum, but sum is implicit. When I write this one, this means ux del x plus uy del y plus uz del z. So, this Einstein notation, if I have repeated sum, then is added. So, this is what I have written. So, this is this one, and this is divergence stuff. So, which I have written in the top. This is coming from pressure term. This is, in fact, this is force feed. Now, what is force times velocity for particles? Is work done, no, work done per unit time is power input. So, it is a power energy supply per unit time by force to a unit volume. Okay. So, this is called energy injection rate, kinetic energy. So, if you like kinetic energy injection rate, okay. And the last term is dissipation, because viscous times velocity is a viscous force. So, dissipation by viscosity. So, we can simplify further, which this identity I will not prove it, but is there in the notes. So, it is nice to rewrite this one u dot Laplacian u as this minus omega squared and that. Okay. And many times you will see this appearing in the dissipation term, but this u dot Laplacian u is not equal to minus omega squared. Okay. So, this derivation in notes is quite simple to derive, you will find that is the case. So, we replace this by minus nu omega squared, okay. And this divergence is one of the term which is absorbed here, divergence here. So, this will become, we can write either in terms of u dot Laplacian u or in terms of minus nu omega squared. Okay. So, you will find that there this term divergence term will become 0 if I integrate over the whole volume. Okay. So, I am going to come to that in the next slide. So, in the integral form, so what I showed you as a differential form, derivatives, but integrate this the old form to any volume, okay, not the total volume, integrate any volume. So, the first term is d by dt. So, this is coming from the old slide. Now, by the way, I am not using partial. Why am I not using partial? I am using total, because this is not function of x anymore. This is energy of a given volume. Okay. So, I use total of a given volume. Now, what about the next term? So, remember it was divergence of u squared u. So, now what is the theorem? It is called Gauss theorem. Using Gauss theorem, I have replaced the volume integral to surface integral. Okay. So, if you recall, that was divergence of u squared by 2 u vector. Now, I integrate over volume. So, by the dr means volume, this is a notation which you follow. Various people follow various notation, but it is in physics, this is quite common, that we write d vector r, that means it is a volume integral. So, it is dx dy dz. Some people write dv, but I do not use it because this v, some people use it for velocity. No? So, I just follow this d vector r, this means volume. Now, this is coming from Gauss theorem. So, this is divergence of a vector, dr is vector dot ds, and this is over the closed surface. This means closed surface. So, I do this flux over full surface. I have to integrate over the full surface. So, by the way, this is flux of kinetic energy. Now, this is important, which I am not going to emphasize in present course due to lack of time, but for any scalar quantity or any vector quantity, we can define flux by phi u cap. This is for fluid mechanics. Now, electrodynamics, there is a different definition. For fluid, this is flux is the scalar quantity or the vector quantity carried by velocity field. So, it will be that quantity crossing per unit area per unit time. Okay. So, this is flux of the quantity in real space. Now, we will do some other flux which is energy transfers will be in Fourier space, but that will be different. Okay. So, this is flux. So, instead of phi, this u square by 2 if I put is kinetic energy flux. Okay. Density is 1, again I emphasize density is 1. So, u squared by 2 is kinetic energy. Okay. Is that clear? Now, this is one is Pu. So, it is a pressure flux, pressure is convected. So, pressure has in this rho equal to 1 language, it has same dimension as energy. Pressure is rho u squared. So, rho is 1. Okay. Now, this is energy supply rate by external force and this viscous dissipation. So, this is all integral form, the earlier one is called differential form. Now, we can go to conservation laws. So, this integral I am going to do over the whole box, kinetic energy integral. So, let us take a special case when the force is external force is 0. External I particularly mean one which is not pressure other than pressure gradient and viscous. Okay. There also a force on a volume, a force on a fluid element, but we mean this Fu means some gravitational force or magnetic force. So, this force I mean Fu. Okay. So, this any external force or in engineering they call body force. Okay. This force is 0, let us assume that, and we assume that viscosity is 0. So, that means dissipation time is gone. With this, what do I get? So, this is called inviscid approximation. Viscid is viscous, inviscid means without viscosity. Okay, inviscid, this is a technical name. Now, I integrate this over the whole volume. Now, this is volume is full volume, not arbitrary volume. This could be box, cylinder, sphere, whatever you may like, but this full volume. Okay. Now, these are the 4 terms which you had, but these anyway are 0 because I assume make the assumption this Fu and u. This is copied from the old slide. Now, we have only 3 terms. Yes.
Are we assuming that the volume we are considering is not changing with time?
Yes, it is a total volume. Volume does not change with time. Yes. So, that is why the d by dt does not act on dr indeed. So, now we will make another condition. So, one condition, these 2 conditions are already there. So, in addition to these 2, we make another condition on the boundary condition. So, this cube or cylinder, we assume that periodic boundary condition. For cube is easy to see, for cylinder it may not be easy for like cylindrical wall, but vanishing means the velocity is 0, vanishing means u is 0 at the wall, at all walls. Periodic means for cube is easy to see, this wall and this wall have same velocity at a given point, right, periodic function. So, if I just go along x direction by 2 pi by box length, I get the same value along y along z, or you could also have the combination. So, periodic along x, but vanishing along y or vanishing along z. So, any combination of this. So, if I have this, then what happens, periodic or vanishing. So, what happens to this term? If it is vanishing is easy to see, this term will be 0 because u is 0 at all the walls, right. This term also will be 0 because both p and u are vanishing. Well, it is u is vanishing, sorry, p I can, u is vanishing. So, both the terms become 0. So, vanishing you can easily see these two terms gone. What about periodic? Periodic, whatever contribution I get from one wall gets cancelled by the other wall. For one wall velocity is going out, another wall velocity is coming in. So, this integral u, one has positive sign, another one has negative sign. Okay. So, this is cancels. So, that is how periodic walls also give 0 contribution. So, the surface integrals vanish for periodic or and vanishing boundary condition. It could also have combination, but combination means periodic along pair. So, is periodic along x, of course, that means periodic has to have periodic along which direction, x direction or y direction, or vanishing along z direction. So, combination is also used. So, we use that combination.
So, vanishing means, I mean, it is like some confinement or.
So, in this room velocity at the surface is 0. So, the fluid flow inside this room is confined. Okay. In fact, velocity must be 0 at a viscous wall. Okay. Viscosity makes the fluid flow having a 0 velocity at the wall. Okay. In fact, it is natural, and vanishing boundary condition is natural for solid walls.
But velocity may be tangential to the wall, maybe.
No, for viscous boundary layers, for real solid walls, all the components of velocity must be 0, all 3 components. The vertical velocity, okay, so let us take a wall. Vertical velocity must be anyway 0, right, because it cannot penetrate. The horizontal velocity here is because of viscosity. So, viscous stress makes the velocity 0 at the wall. Okay. Of course, away from the wall it becomes finite, but at the wall viscosity makes it 0. So, as a result, what do I get for? So, these 3 conditions, external force is 0, viscosity is 0, and we have this boundary condition, then we get u squared by 2 dr is 0. The integral over the full volume is 0. What does it mean? U squared by 2 integrated over the whole volume is a constant. Okay. So, that means kinetic energy in a box is conserved, means it does not change with time. Okay, it will remain the same. So, this is conservation of kinetic energy for fluid flows which are inviscid, that means viscosity is 0 and there is no external force, and of course, it is vanishing and or periodic boundary condition. Actually, it should be it can't have both at the same wall, but yeah, it should be and or. Okay, so this we should be. I can't have periodic as well as vanishing at the same time. So this should be clear, no? But anyway, this is a technical English part, but okay, clear. This derivation is important derivation, but these are the steps involved. Now let us look at kinetic helicity. So I give the definition of helicity is half u dot omega. I have to integrate over the whole volume. This one. Now I need to take the derivative. Now since my dr is not changing, this dr volume, so I take a small element. Now since dr is not changing, I do not take derivative with relative to dr, but I take total derivative with relative to the function u dot omega. Okay. Now this will total derivative d, capital D. Okay. So again I apply product rule. So product rule will be omega, then this is d by dt of the first function. So this product rule, right? I mean omega du by dt plus u d omega by dt. Now what is du by dt? Now again inviscid approximation. Huh? So assume force is 0 and viscosity is 0. So what is du by dt? So you can look at your notes, is minus grad p. So this is u dot plus u dot rad u. So this is minus grad p because viscous term is 0, f is 0, right, and rho is 1. So this one is minus grad p, first one. And what was second term? So it is, we have done this before. Is no, it's not 0 for 3D. Stretching term. This one, omega dot grad u. This is the term. Okay. So this is minus grad p and this is omega dot grad u. Now what about this first term, this one? Since del dot omega is 0, right, divergence of omega is 0, but that is straightforward because divergence of a curl of a vector is 0. So we have del dot omega is 0. So if any of this condition is there and divergence free vector can be pushed inside. Okay. Now is simple algebra that you can also push both inside. So this can be written by following the similar steps which I did for the last derivation. It is divergence of u squared by 2 omega vector. Okay. So this I will leave it as for you to derive. It is following pretty similar steps, but please cover this, do it yourself. So this is what we will get. So this is the first term is here, second term is here. Now, I apply Gauss's theorem again. So, divergence of this dr, what will that be? By Gauss's theorem is u square by 2 omega dot ds, okay, and the first term will give you this, one will give you this. So, it is just Gauss's theorem. Now, for vanishing boundary condition or periodic boundary condition, what this will be? So, u is 0 or omega is 0, periodic boundary condition will give you, okay, and so this thing is 0 for this term is 0 for periodic or vanishing boundary condition, okay. So, we get 0. So, kinetic elasticity 2 is conserved for 3D flows, okay. So, this for 3D. What about 2D? In fact, 2D, what is u dot omega? 0. So, kinetic elasticity itself is 0 trivially, okay. So, 0 remains 0, it does not change. So, that part is obvious, okay. So, go to the next slide. So, let us look at insta-phi, is it conserved or not, okay. So, we will go step by step. So, we start with insta-phi equation. So, this is, well, we start with first what is it equation. This I derived it in the last lecture. I dot product this one with omega. So, the first term is straightforward. So, first term is that, okay. Now, I in fact I have to save steps, I already written in the integral form. So, this is this term will give you this one. Now, I am not deriving it, but you can easily derive, and the third term is this. Now, this term can be written as divergence of a vector, and that is how I converted using Gauss's theorem to a surface term, but this term cannot be written divergence of that form, okay. There is no, if there was u, it would have gone in, but there is omega dot omega, you try it, you cannot convert it to divergence of a vector, okay. So, for periodic and vanishing boundary condition, similar way, this term will go to 0, okay. This term conserves, but this term will lead to well, for conservation we want both the terms to go to 0 for the whole volume. The first term will go to 0 for periodic and vanishing boundary condition, but the second term does not. In fact, second term is a vorticity stretching term. So, as I said, you know, this vorticity, if there is a velocity field, that will stretch the vortex. So, that way vorticity becomes thinner and omega squared increases, this vortex tube becomes thinner. So, this second term does not become 0 for the whole volume, and that is called vortex stretching term. So, that is why in 3D this omega squared by 2 integral is not 0. So, insta-phi is not conserved in 3D, okay, it is straightforward this one, but is it conserved in 2D? So, what happens, what is this term u dot grad u? 0, because omega is along z direction and grad is along x direction, no. So, this omega dot grad is 0. So, in fact, this vortex stretching does not happen in 2D. These are infinitely long vortex tubes which can only move, there is no uz to stretch it. So, for 2D the vortex stretching is 0, as a result omega squared by 2 is 0 integral. So, omega squared by 2, this integral is constant in 2D. So, insta-phi is conserved in 2D, okay, in 2D conserved, but not in 3D. So, summary is kinetic energy is conserved for both 2D and 3D. Kinetic elasticity is conserved in 3D. Of course, it is 0 trivially in 2D. So, but insta-phi is conserved only in 2D, not in 3D, okay, for pure hydrodynamics, inviscid hydrodynamics. Now, these are three very important quadratic conserved quantities. So, you saw all of them are product of two vectors. Now, there is a quantity called circulation which is not product of two vectors. It is a very important quantity, and so it is defined like this: for a closed and co-moving contour. Co-moving means it moves along with the fluid. So, just think of, you know, this cigarette smoke. and you just follow that smoke, one fluid parcel. So you make a contour. So I have a picture here. So this contour, your particles are sitting here, or the fluid elements, and when the fluid element moves, your contour will also move with it. So this contour moves along with the fluid parcels. I will not call particle, we are not thinking of particle, but it moves with the fluid. You tag this fluid element. So this is called co-moving, you move with the fluid. Okay, you hang on to the fluid and move. So for this contour, I have velocity field at every position. There is a velocity field, u field here. So I take a dot product. So u dot dl integral over the whole closed loop. It should be closed loop. So this is a closed loop here. I integrate over the whole loop u dot dl, and this is called circulation. So circulation of velocity you can think of. So velocity you have to integrate at every small line elements and you just sum it up. Now I can use Stokes theorem. So what does Stokes theorem says? This line integral over the closed loop equal to surface integral for any surface whose edge is this contour. It is not a closed surface, it is open surface. So you can think of a cap. So the cap's edge is what we have here, cap's edge, and the cap surface, which can be moved anywhere you like. In fact, this really is a topological result. It is true for any surface, as long as the surface edge is same as this closed curve. So this is omega dot ds, and this ds, the surface, actually whole surface, is the one whose edge is the contour. It is not a closed surface. Okay, so I am not writing a closed stuff here. It is open surface. Now this is circulation. Now it turns out for inviscid flows, viscosity is 0, this quantity is also conserved. Now this is not a quadratic invariant, but this is one of the important theorems, and this conservation law goes to Kelvin. Okay, so this is called Kelvin circulation theorem, and according to Kelvin circulation theorem, d by dt of u dot dl, this one, if I will show it to be 0, the proof is quite straightforward. So there is one difference between the earlier proof and the present proof, is that this dl line element is changing with time, right, because my fluid element is also changing. So my time derivative will act on dl as well. Earlier my dr was fixed when I was doing integral. My quantities were changing with time, but here now dl itself is changing. So we have two terms. First one is what used to be there in the first three slides, earlier three slides. So the second term is coming from d by dt acting on dl. So if I have product rule, I have to apply d by dt on both, whatever is changing, right? I mean, this is straightforward product rule. So now we can just put in, okay, but this is straightforward. No, d by dt is minus grad p. This is easy. But what about this second term? Second term is bit tricky. So the derivation, I will show you one derivation. Is this is dl, okay? Dl vector. Vector is a dl. So there are 2 points at the two ends, A and B. So what is the dl? It is Ra minus Rb. Okay, so I have it here. So this is Ra minus Rb. Now I take the time derivative of that. So there will be Ub minus, so I am sorry, I made a mistake, Rb minus Ra. dl is Rb minus Ra. This one, this is Rb minus Ra. If I take the time derivative, will be Ub minus Ua. Now what is Ub minus Ua for a small element? It is du, and velocity changing at these 2 points, which is dl dot grad u. Okay, so u is changing. How much does it change with dl? This is dl dot. So you can look at dux. Well, how much dux changes? It is dux x dx plus dux dy plus dux dz dz, right. This is ux is changing is 3, okay. Now, what is this one? This is dl dot grad ux, same thing for ui and uz. So, this is precisely what I have written here, okay. So, this is just that. So, I have already got the answer for this one. So, now let us combine this two sums. So, I will get first one is minus grad p dot dl, and second one is I just written it here. Now, first one is trivial, this guy, no, what is this one? Grad p dot dl. So, there is a gradient and I go distance dl, gradient in any direction, and the gradient could be here. So, grad p dot dl will be dp. This bit of vector algebra, but no, this is fine or not fine, okay. So, this is dp by dx times dx plus grad p dy dy like this. So, what is this? This is just dp, change of p at two positions. So, this is just vector stuff. So, first one is minus dp. Now, I have to sum up this dp over the whole closed contour, dp, 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 dp. If I go over, how much will I get? What is the net change? I go around, I come back to the same point, and these are vector sum, scale, well, algebraic sum, not algebraic sum. So, pb minus pa, then pc minus pb, and finally I come back. So, this term is 0 when integrate over the whole closed loop. This one is straightforward, is dl dot grad u squared by 2, this one. So, u can be pushed inside. Now, be careful, sometimes can be pushed, sometimes it can't be pushed. So, here the u inside and u outside and can be pushed, you can check yourself. And so, this will be basically du squared by 2, same idea, go around, you come back to same point. So, this d of any scalar is 0 when I sum over the whole loop. So, this sum is 0. So, what does it mean? This circulation does not change with time, is conserved quantity, okay. So, this is also useful result which we will use it later when I do more of MHD. In fact, we will use some of this in MHD and so on. Okay, so, these are the 4 conservation laws I discussed today. Kinetic energy, kinetic helicity for 3D, and then kinetic helicity and entropy for 2D, and then circulation. So, this ends. Thank you.